Okay, right, I think we ready to start. And we will start exactly where we left yesterday. Buongiorno. So we are talking about the geotechnical design of shallow foundations. We said right in the end yesterday that the overall load displacement, vertical load, vertical displacement of a foundation, of a real foundation, looks a bit like that. It is highly nonlinear. It is non-elastic. As you can see, when you unload, when you remove the load, you recover only very little settlement, as you can see from those all unloading, reloading lines along the curves. And essentially you never reach a final value, but the more you penetrate into the soil with your foundation, the higher is the load supported by your foundation. So having this in mind, we have now to try to design our foundation, taking into account that we will separate from this general overall behavior, we'll separate the ultimate limit state in terms of bearing capacity, in terms of ultimate resistance of the soil, from what is the response of your foundation under working loads, exercise loads. And it is a matter of a serviceability limit state. Okay, this morning we will focus on the first part, the ultimate limit state, the definition, the determination of the bearing capacity of a foundation under initially a vertical load and subsequently under general loading conditions. Now, talking about ultimate bearing capacity, we have to devise what is a possible failure mechanism. So we are trying to simplify as much as possible our problem, and we have a ground surface, a horizontal ground surface. We have a shallow foundation, which is a footing bedded in the shallow layers at a depth D of breadth B, subjected to a uniform pressure named Q. So what is the possible collapse mechanism, not of the foundation structure itself, but of the soil which lies beneath our foundation? Okay, so let's try to think of the possible mechanism that occurs into the soil when you increase the load until you reach the limit of the soil resistance. To do so, we can make use of different approaches. One of these approaches is the limit analysis, about which we will probably listen a bit more from Professor Marchi, but that here it is recalled in general terms. So the limit analysis makes use of plasticity theorems, essentially a lower bound theorem and an upper bound theorem. Both theorems can provide us with exact solution within their limits, within their assumptions. Now, the lower bound theorems will provide us with the possible limit load, which is, as it says in the theorem, a lower bound. So that is the sort of the minimum that you can get. The upper bound works in the other way and provides a sort of a maximum limit, and the true solution is in between the two solutions provided by the two theorems. So for applying such theorems, a collapse or a failure mechanism should be assumed. Therefore, let's try to think also in physical terms what is a possible mechanism which occurs in the soil under an increasing load, as I said. So this is the possible mechanism, which is called as a general shear failure, and it is valid for soils of low compressibility, such as dense, coarse-grained soils, or if fine-grained soils fully saturated in undrained conditions. Okay, so you should remember that if you have a saturated fine-grained in undrained conditions, this means constant volume. Constant volume allows only shape variations because the volume is constant. And so it is, in the short term, it is very stiff, very rigid. So either a dense coarse-grained soil or a fine-grained soils in undrained conditions, we have to think that the soil below your foundation is very rigid, is very little deformable. So once you increase your load and your foundation tends to penetrate into the soil, but the soil is not prone to be deformed because it is, as we said, relatively very stiff. So at some stage this increased stress into the soil will reach the limit shear strength of the soil, and this will be reached along the formation of possible slip lines that you can see drawn into the sketch. So this is a bit animated to let you understand that a rigid wedge, there is the formation of that triangular wedge below your foundation, which is somehow attached to your foundation and will penetrate into the soil. Continuous failure surfaces develop between the edges of the footing and the ground surface. So the only way to let the footing goes into the soil, which is not as I said, prone to deform, is to displace the soil. And in order to displace the soil laterally, you need to reach the failure limit, so that the soil can slip along these surfaces. Now, if you look around, if you follow around the arrows, the red arrows, you can see that the footing tends to go down, and the soil moves laterally to allow the footing enter into the soil. And if all this mechanism, because the soil is very rigid and the volume is pretty constant, the soil which moves laterally has to come out as a sort of a heave at the sides of your foundation, because you have this footing going down, the soil moving laterally and upwards. Okay, overall we have almost constant volume. Okay, so this is a possible mechanism which is likely to occur for rigid soils, as I said. It's not the only one. We now will see other possible mechanisms for other soils, but this is relatively clear, and so this is what we should have in mind when we will define a possible maximum load. Because if you have this scheme in mind, then we have to find the limit equilibrium at which you reach this mechanism, and that is the limit bearing capacity of your foundation. So let's read together that the state of a plastic equilibrium is reached initially in the soil around the edges of the footing, which subsequently spreads downwards and outwards. Heave of the ground surface occurs on both sides of the footing, although in many cases the final slip movement occurs only on one side, accompanied by tilting of the footing. Now, this final sentence says that essentially in theory you have a perfectly symmetric mechanism. In reality, nature is never perfectly symmetric. So once you have established this possible mechanism, the footing will end up to go one side more than to the other, so will tend to tilt and will tend to follow one direction instead of the other. But this is after you have established this full mechanism into the soil. So actually where it actually goes, the footing after failure, is not that relevant. The important thing is to determine which is the maximum load before the failure mechanism. Now, in the case the soil is some more compressible, like a medium dense coarse-grained or a lightly over-consolidated fine-grained soil in drain conditions, so something more compressible than the case before. The soil, the compressibility of the soil can allow the foundation to go into the soil by reducing its volume and producing settlement. At the same time, you will have the initial formation of a mechanism which is similar to what we have just seen. It is possibly not fully developed. The heave is reduced with respect to the previous case, and so you have something, an intermediate situation in which the soil can be compressed a little bit and you have the formation of a mechanism which is not fully developed. So significant compression of the soil under the footing and only partial development of the static or plastic equilibrium. The failure surfaces do not reach the ground surface and only slight heaving occurs. Tilting of the foundation is not expected because you have not a full development of a mechanism. But if you follow the red arrows, you can better understand. Now, as a third and last mechanism, you are on the other side, in which the soil tend to be more compressible and will accommodate the full displacement of the soil. So once you push your foundation into the soil will deform, will develop shear failure at the edges and allow the footing into the soil. And this without necessarily generate a mechanism, because you no longer need to move the soil sideways and you don't need to displace the soil. You can compress it. Okay, it is a matter of really of a physical mechanism. Now, in this case, we call it the punching or punching shear failure. And this is valid for loose, coarse-grained soils or compressible fine-grained soils in drained conditions. This mechanism occurs for highly compressible soil under the footing, accompanied by shearing in the vertical direction around the edges of the footing. There is no heaving of the ground surface beside the edges, no tilting of the footing. Relatively large settlements are a characteristic of this failure mode, and the ultimate bearing capacity is not well defined. So if you have followed me so far, this corresponds more or less to the load settlement curve that I showed you in the first slide this morning. Okay? So a continuous increase of the load, a continuous settlement, you never reach the definition of a full bearing capacity, and this is what you typically expect for a compressible soil. So we have understood, let me go back to this slide. This is what you get out from a punching mechanism, which is typical, as we will see, for deeper foundation, but you might have also a well-defined mechanism, for general shear failure in which you have a peak load. So let me show you. This is a possible what you get from a centrifuge testing, for example, as I mentioned yesterday. Let me show you what you can have according to the different failure mechanism. Now, if we talk about general shear failure, that is reminded in the sketch just above, you see the load settlement curve on your foundation looks a bit like that. So this is a different with respect to what we have just obtained in a centrifuge. You get to a limit in which you have the full development of your mechanism. That is sort of a peak load. After it, you have the full movement, the displacement and the tilting of your foundation. And so you have a sort of a softening behavior. You have a reduction of the load sustained by your footing. But in order to generate this mechanism, you have to reach this peak load. And this will be definitely our bearing limit. This is clearly defined. So when we think of a general shear failure, we are looking for this value, for this peak load. Okay? Now, when you move to local shear failure, or even more to punching shear failure, you see that your load settlement curve does no longer show a peak. So it is, and it looks like the curve we obtained in the centrifuge. Now, as we already mentioned, now it is more difficult, or let's say almost impossible, to define a precise maximum load, because there is no maximum load. The more you penetrate, the more load you develop. So the bearing limit, the ultimate limit state of your foundation, will be defined in terms of maximum settlement that is allowed. Okay, because you don't want to go to penetrate too deep into the soil, and so you want to fix a limit load. But the definition of such a limit load is not uniquely determined. It's a bit awkward, because you define a maximum limit load, a bearing limit, defining a maximum settlement. So you define a maximum load, but you have to define a maximum settlement in terms of deformation. We have no alternative, because this is what happens in real soils. If you look at the right-hand side plots suggested by Vesic now almost 50 years ago, this is what you get for coarse grain soils. So we are always in drain conditions. Forget the distinction between undrained and drained conditions. We are in sand, for example, and you see the three mechanisms are reported in this chart, and you have general shear failure here, local shear, and punching shear. And on the x-axis here, on the horizontal axis, you have the relative density. And in fact, if you remember, we have just mentioned if you have a dense sand, this is general. If you have something intermediate, it's local. If you have a loose sand, this is punching. So you can, and because the density controls the compressibility of the soil. So the denser the soil, the stiffer it is. And so this is what we have just said. But on the vertical axis, you have the relative depth of your foundation. So dF is the depth, and this won't reach a higher value because we are talking about shallow foundations. So yesterday, for example, we said Terzaghi will put a limit of this ratio to 2.5. This can be considered even 3 or 4. It's still a shallow foundation. We said this is not cannot be fixed in geometrical terms, but you can see that the deeper you go, the more you tend to develop a punching shear failure. Once you reach, for example, the ratio of 4.5, for any sand density, you have a punching shear mechanism. So if you look at the possible general shear failure, which is the only one for which we can define a real peak value, so a well-defined bearing capacity, occurs only when the sand is very dense and when the footing is relatively shallow. Only this part of this chart is concerned with general shear failure. This is important to stress because this possible trend is the only one which allows us to define a final value, a bearing capacity. And this is what we will find out with our formula. In the end, I will show you there is a very simple formula by which you define a bearing capacity. But that is referred to this mechanism, general shear failure mechanism, which is not the only one, and it is not the most common that you can have. But it is the only case in which we can define by equilibrium or by the limit theorems which I mentioned, you can define a single bearing capacity value. So let's have a closer look to these plasticity theorems. The lower bound theorem, if there is a stress field such that equilibrium equations are satisfied and the stress do not exceed the yield condition, the collapse cannot occur. So as far as you can define this situation, you know that your total load is safe, is below the maximum load before failure. Okay, you don't know how below this is, but you can say, you can tell that it is safe. I won't go through all these tests. You can have it. You can have a look at your slides. But essentially, you end up with a lower bound solution. So the good thing is try to develop a stress field, which can be in principle any stress field, as long as it is in equilibrium, and you have to find the stress field which provides you with the maximum possible load. And that is, you are certain that this will still be a lower bound solution. On the other side, if the rate of work of external loads equals the rate of internal dissipation, then the collapse must occur. And this will define you with an upper bound solution. Once again, you can define any mechanism, you can define any equilibrium between the internal and the external workload, and the lower it is, the closer is to the real actual solution. Now, this sounds a bit abstract. It should be applied to real cases, like the case of the foundation, but we won't have time to develop. I will show you only just a few slides to see how this works, and if we have time with Professor Macchi, this will develop in a separate section. But I don't want to lose the track of the presentation concerning shallow foundation. Now, important thing is that the main assumption for the validity of these plasticity theorems is that the soil is a rigid, perfectly plastic material, which is, of course, is not true, but that is sensible for the problem we are trying to face, to deal with, but it must be with an associated flow rule, and this is typically not the case, especially for sands. Now, this looks similar to what I showed you last week in terms of undrained and drained behavior, and this, of course, is also the case for the foundations. So this is not related to a single soil element, but to the foundation problem. And so if you apply, you have a sort of a straight increased load, and then you have a constant load. So this is the external load, the total stress that you apply by your foundation. This will generate a pore pressure, excess pore pressure, that will start to dissipate, and the effective stresses will correspondingly increase. Now, during this process, this consolidation process, you have the volume reduction and the settlement of your foundation, and so this means that you have initially undrained conditions, and then you reach out drained conditions. So the same thing that we introduced last week for the soil elements and for the load paths is also what occurs for a foundation under a general pressure, increasing pressure Q, and with time. So if you want to plot what you expect the settlement with time, you think that you have possibly some initial settlement at constant volume. Then you have the consolidation settlement, which is due to this reduction of volume, and then at the end of the consolidation you might have some secondary creep settlement which goes on forever with time. So when because we have two problems, we have to define the bearing capacity and then the settlement. And as you can see, the settlement is a function of time, and it is it comes out as the sum of three contributions, which is the initial, consolidation, and secondary settlement. So in undrained conditions, soft clays and we have, we said, constant volume conditions, and so we are we can think of a general failure mechanism undergoing. Now, this is just a reminder of what happens in undrained conditions. No change of water content, total stress analysis, and you can express the failure criterion of your soil in terms of the Tresca expression. So you have this. Okay, this is just to remind you, because in order to define the bearing capacity, the limit of your foundation, you need to define what is the limit resistance of the soil. If you are in undrained conditions, you need to define your failure criterion. And in undrained conditions, this is our Tresca criterion. Okay, so this was just to remind you that we will make use of this failure criterion in undrained conditions. Let's try, once we define the failure criterion for the soil, let's try to apply our plasticity theorems for the soft soil in undrained conditions. Now, I have left only one possible kinematic mechanism to apply the upper bound theorem. Okay, so you have your footing here. You apply some vertical settlement because of the load. This is rigid, so in order to let this go down, this have to move laterally with this direction. These are velocity vectors because this is a kinematic mechanism. You have some transition in between these two. This is going sideways. This is also moving sideways, but also with an upward component. So if you look at this mechanism that we have constructed in order to apply the upper bound theorem, this looks very similar to our general shear failure mechanism. So this is why we introduced first the general mechanism, because this is what we had in mind that could happen below your foundation. Now, the transition zone between these A and B areas can have different shapes, can have different expressions, and I won't go into the details of the analytical details of this construction, but just to show you how this can be constructed. Okay, so let's have a look just in general terms to this mechanism. You have to equalize the external work to the internal work, as we mentioned before. If you follow the analytics, then you end up with this expression. Okay, so as I said, let's forget, we have no time to go into the details, but you can follow, if you wish, all the expressions which are reported in the slide, and that is what you get in the end. Okay, so by Q limit, let's be certain that we understand we have a footing like that, you see. In this case, the footing is considered bedded on top. This is not necessarily the ground surface. Actually, we said that this is the ground surface, and your footing has to be placed at a specific certain depth, D or DF, what we call. Okay, so this is not exactly on top of the ground surface, but in our scheme we remove this soil, we get rid of this soil, and we just consider the contribution in terms of surcharge loads. Okay, so we can build a scheme in which there is no soil above the foundation level, but of course, since there will be some soil, and that soil provides an important stress contribution, we, as you see on top, we substitute this soil with its overburden contribution, which is Q gamma, which is the gamma of this soil, times dF. So we have now this scheme. No soil at the side, but an overburden stress, and the footing where you have a increasing pressure provided by the superstructure, which is our Q, that gets to a limit. So we are looking for the limit load at which we develop a full general mechanism into the soil, which is something like that, as we have seen before. And we can build a proper mechanism, like the one in which you define all your curves, you have an analytic expression of your curves, you equalize the internal work, the external work, and you end up that your Q limit, if you express the shear strength of the soil with the Tresca criterion, so you say that tau is SU, you end up that the limit load is a function of your SU and also of this Q, which is the overburden stress, which provides a contribution to your limit load. So if I copy that, you see that this is Q plus 2 plus pi. The fact that this is 2 plus pi becomes from the analytical part SU. And if you call this bearing capacity factor NC, you can write, simply write Q plus NC and SU. So we have, in this way, got an expression of the limit load, which is, according to the upper bound theorem, is an upper bound. Is not exactly the true limit load. And but we notice that this is a function of course, the undrained shear strength of the soil, of this bearing capacity factor, which is 2 plus pi, so 5.14, something like that, and the contribution of the overburden stress, which tells us that the deeper is the foundation, the higher is your limit load, because if you increase this dF, you increase this, and you increase your limit load. So this is the first result where we can get. If we look on the other side to a lower bound solution, which is a stress field, which is in equilibrium and never reaches failure in any point, this is a possible way of doing it. Once again, I won't go through all the analytical part, but you can see that we have a similar scheme. We have the foundation on the right hand side reaching a Q limit. You have the overburden stress, which is this one, and then you have the stress field, which is separated between the soil beneath the footing and the soil outside. You have to establish the equilibrium between the two, and you end up with another solution provided for the same situation, but making use of the lower bound theorem, getting to an expression which is Q plus 4 SU. Okay, very similar to this. This is an upper bound, this is a lower bound. The true load under this assumption is in between the two. Okay, so the better we are, the more able we are to match the two theorems, the closer we go to the exact solution. Remember, always an exact solution under the assumption of the plasticity theorems. Now we can think of a more precise, a better defined stress field, like this one, and of course you have to find equilibrium in all that regions. That's why analytically is a bit longer and we are not going to the details. But the good thing is that in this case, under this assumption, in this case, we get to a lower bound which is equal to the upper bound. And this means that this is also the true solution. And so we know that if the soil's shear strength is expressed by the Tresca criterion, if we think that we are with an associated flow rule, all the assumptions we have introduced for the plasticity theorems, this is the exact solution of the limit load of your pressure. And this is a good initial point. Now, of course, you have also drained conditions, and in drained conditions, which are reminded here, we can see that these are drain conditions because you have no pore pressure development. You see that your pore pressure stays constant, and so you develop settlements at the same time you increase your load. So this is the typical situation of a drain conditions. In that case, you can no longer express the shear strength of the soil by the Tresca criterion, but you have to use the Moore-Coulomb criterion in effective stress terms. And so you won't find the same solution. So what is the limit load in drain conditions under this Moore-Coulomb criterion? And then, if you also, for to do this, you have to consider also the soil weight, because this effective stress of the soil here depends also on the weight of the soil, which according to the Tresca criterion, this is not considered, because you do not have any soil stress in this expression. So once you move to the drain conditions, and you have to consider also the soil weight and the gravity, you are no longer able to find a true solution, to find the match between the upper bound and the lower bound solution. You have to consider separately the different contributions. But you can apply, instead of the plasticity theorems, you can apply the limit equilibrium solution, and you can find the equilibrium between a possible Rankine active zone and the Rankine passive zone on the right hand side. You remember yesterday we have reminded that what is an active, a Rankine zone and a passive zone. Okay, so essentially, why do we have an active zone below the foundation and a passive zone laterally? Why it is not the other way around? Because think about once again about the mechanism, the physics of phenomenon. If you push the footing inside, we said the soil is expanding, is moving laterally to allow the footing going down. And the expansion of the soil is exactly what we referred to yesterday. The lateral expansion is something which provides you with an active zone. Now, if the soil is expanding laterally below the foundation, will compress the soil, which is at the side of your foundation. So if from this side you have an expansion of the soil, getting to an active condition, on the other side you have a compression of the soil, getting to a passive zone. So this is consistent with the mechanism we have just introduced and with what we have said yesterday about the ranking zones. We know how to consider the stresses according to ranking theory, because we know Ka, we know Kp, and we can write the equilibrium on the right-hand side. Now, if you look for the horizontal equilibrium between the active zone and the passive zone, then you end up with an expression which is written on the right-hand side, which I will copy here. This says that the Q limit, the limit pressure, the bearing capacity for a general failure mechanism, which is this one that we have already discussed, is given by the sum of three separate different contributions. The first one is 1/2 gamma B and gamma. The second one is C and C, and the third one is Q and Q. Now, we have to understand what are these terms. The cohesion comes from the Moore-Coulomb criterion. I have cancelled it, now let's go write it again, which is C prime and phi prime are our shear strength, soil shear strength parameters in effective stress terms. So this should be written as C prime, because we are following this criterion. Gamma is the weight of the soil below your foundation. B is our footing breadth. N gamma, NC, and NQ are all called bearing capacity factors. And you see, following this theory, have a specific expression. This is something that we know how to consider. We know how to compute. Now, once again, this is not the exact solution, because it was derived in these conditions. There is no match between the lower bound and upper bound theorem, so it is something which is approximate, but is valid for all conditions. Drained, undrained, considering the soil weight. So this is something which is not exact, but approximate enough. And you see, you have these three contributions, where N gamma, NC, NQ are called bearing capacity factor. If you assume a different expression and different analysis, you will end up with different expressions of N gamma, NC, and NQ. But they are all function of what? As you see there, they are function essentially of Ka and Kp. Now remember, Ka is the active earth pressure coefficient, which according to ranking was 1 minus the sine of phi, 1 plus the sine of phi. And Kp is 1 over Ka. So it is also a function of phi. So essentially, in Ka and in Kp, there is phi. the shear strength angle. And in fact, the most important parameter, which is the shear strength of the soil beneath your footing here, does not appear explicitly in this expression. And this is a bit, at the first instance, this is a bit awkward. Where is the shear strength here? The shear strength is in all the three bearing capacity factors under these specific expressions or other expressions, which are always function of phi anyway. So, of course, phi is the main parameter, and phi provides you with the expression of n gamma, n c, and n q. Now, this subscript gamma, c, q refers to the fact that this is the bearing capacity factor which refers to the solid weight, gamma. This is the bearing capacity factor which refers to the cohesion, C prime. This is the bearing capacity which refers to the overburden pressure, this Q, which is this Q. Now, if you have here the soil is fully saturated, this Q should be considered as an effective overburden pressure. Okay, gamma dash. Then when we will, in the exercise, we will understand what is the effect of the position of your water table and which is the right gamma or gamma dash that you have inserted in this formula. So this is what you will use to get the bearing capacity of your foundation. And as you see, this is relatively simple. And we could have started just writing this expression and saying, well, you will consider the bearing capacity with this formula. Now, two things. One thing, we want to know where this formula comes from, and we have more or less understood that. Second thing, we have to know that this is an expression which is valid and was derived for a general shear failure mechanism, which is not the only possible mechanism of a shallow foundation. So you have to make use of this formula in a careful way. But we have no alternative, because as I said, all the other mechanisms do not show a clear, unique value of limit load. So we will always refer to this limit load where you have the main shear strength parameters, C prime and phi prime. But we can see that the bearing capacity of our foundation depends on C prime and phi prime, but there are other parameters which matter. For example, the overburden stress, we had already noticed here, is important. So once again, the deeper your foundation, the better it is. Now, of course, if you want to build a shallow foundation under 4 meters instead of 1 meter, it's more complicated. You have to excavate 4 meters. You have to. It's all more complicated and more expensive. So this is an important contribution to the bearing capacity. But you have to consider if you really need it. The cohesion terms can exist or not. Because, for example, for a sand, which is a cohesionless material, typically this does not exist and this does not exist. So you are left only with two terms. And if you are in this, consider that you wanted to bed your footing on the ground surface, which is still possible even if not recommended because of the water content variations that we mentioned yesterday, but you can still put your footing on top of a cohesionless soil. Where does the capacity come from? From the only term left, which is this one, because the soil here will always have some gamma, and so this term in drain conditions will never become zero. and you are left no overburden stress, no cohesion. This is there. And you see, this depends on n gamma, which is phi, on gamma, which is your soil unit weight. This is what it comes with the soil, and also with B. What is B? B is the footing breadth. So you say, well, of course, if I have a larger footing, I'll have a larger bearing capacity. This is not exactly what you have in mind, because this is a unit pressure. Okay, so the load, the maximum load that you can apply here, the maximum load in terms of load, of force, this is a Q limit. Okay, the Q limit is this pressure, what you get from this expression, times the area of your footing. And if you consider that your footing is a rectangular footing, for example, you have your Q limit times B, which is the footing breadth, times L, which is the footing length. So it is obvious that the load depends on the area, because this is the pressure. You multiply by the area, the larger is the footing, the higher is the load. But here we are not saying this. We are saying that the unit pressure depends on B as well. So not only on the soil characteristics, but also on the footing size. If you think about, the footing breadth counts twice. Here for the unit pressure, and here as part of the area. So when you say, what is the bearing capacity of this soil, you can't actually answer to this question, because this depends also on the type of footing and on the size of the footing you want to place. So you always should refer to the bearing capacity of your footing on your soil. The two things go together. Now, if you are in undrained terms, and we go back to our Tresca criterion, in which the shear strength is expressed as undrained shear strength, this means that your undrained shear angle, if you remember, is equal to 0. Now, if you put this expression in the expression of Ka and Kp, you realize that n gamma, when phi is equal to 0, which is not your friction, is your undrained shear strength, but if you put phi equal to 0, you end up with n gamma equal to 0, nq equal to 1, and nc equal to something which is like 2 plus pi. Not exactly in this expression, but something very close to this value. So you see that in undrained terms, this is 0, not because gamma is 0, because this comes 0. This is no longer C prime, but it's the undrained shear strength. So you have tau, this is 0, you have SU and C, which is almost 2 plus pi, plus, this is 1, and you have some Q. Q is no longer Q dash, it's the total overburden stress. And so you end up with an expression which is exactly what we had already determined using the plasticity theorems. So this expression, these three terms, are of general validity, can be applied in drained conditions if you use the Moore-Coulomb criterion and the Moore-Coulomb shear strength parameters, and can be used also in undrained terms if you use the Tresca criterion, sorry, this is not tau, this is killing me, of course. If you use the Tresca criterion, you end up with an expression which is still valid. You have just to apply the correct shear strength values to this expression. So we are relatively happy because with all the limitations we have mentioned, we have ended up with a formula which takes us to the final solution. And you see on the left-hand side in undrained, the application of the formula in undrained conditions, and the application of that formula in drained conditions, which I have just mentioned. Now, in this graph, you have the expression of NC, NQ, and N gamma as a function of phi, which is on the vertical axis, provided by Terzaghi. Terzaghi developed this solution and and of course has provided also an analytical expression of these three bearing capacity factors, which are plotted in this graph that we will discuss. Let's now take 10 minutes break. Please, no longer than that, because I would like to complete this topic today. Okay. So what I will say is that this is the trend of our three bearing capacity factor, NC, NQ, N gamma, as a function of phi, shear strength angle, in the solution provided by Terzaghi. And it is immediate to see that when phi is equal to 0, so you are at the bottom x-axis, N gamma is equal to 0, as I had written on the blackboard. NQ is equal to 1, and NC is equal to 5.7, which is a bit larger than 2 plus pi, because this is a solution by Terzaghi, but it's not that different. Important thing, interesting to see, is that the trend of this expression for all the three bearing capacity factors is highly nonlinear. So, especially when you go over 30 degrees, for example, you have phi 44 degrees, and gamma is 260. When you increase phi by 10%, you go to 48, and gamma becomes 3 times greater, 780. So, of course, phi 44 or 48 are very high values. Not impossible, but typically for a very strong, dense sand gravel, you might reach those values. But even when phi is lower than that, these three bearing capacity factors can change a lot. This means that it is very important to select the most suitable, the most correct value of phi. That formula is relatively simple. All parameters are relatively simple to determine. It is valid, once again, only under the assumptions we have recalled in the first part, but then the crucial thing is the parameters, especially the soil parameters, that you insert in that formula, because you can easily get to a value which is twice as much as the other, just because you have a phi value which is different for 1 degree or 2 degrees. Okay, so this is an expression which is very sensitive to the shear strength parameters that you include in it. Another important observation is this one. While we have a general agreement on the expression of NC and NQ, and so there is little variation, when we go to the N gamma value, you see how many expressions, how many authors, how many methods have been used to determine different expressions of N gamma. Typically, they are all function of phi, and this plot provides you with the value of N gamma as obtained by several methods for a phi equal to 30. 30 is a much more common possible value. It's not as great as 44 as before. So this typical common value, phi equal to 30. Delta is the angle of friction between the footing and the soil below, which in this case was assumed equal to the angle phi. And you see, according to the different solutions, different methods of solutions used, and to the authors who have implemented and published their solution, you have limit equilibrium methods, the method of characteristics. I can't remember exactly what is ODE's. I don't want to tell you something not correct. The upper bound solution is the plasticity theorem, the limit analysis using finite elements, empirical formula at the bottom. So anyway, doesn't matter. We don't know exactly which is the method all these authors used, but you see that you have a range of possible values between 15 and 25, which is not as large as we have just mentioned. Still, it's an important difference. And this is, even if you choose the right phi value, you have the need to select one of these solutions, which is the best. Difficult to say because they are using different approaches, so there is not really something which is better than the others. Now I would say that the most recent expressions are probably more reliable because they take into account of all the research before. Typically, you see the solution by Martin, somewhere Martin, 2004, 2006, certainly are certainly among the most reliable, but I'm not really suggesting which one you should use. You will tend to use also the conservative solutions, the one which provides you with a lower value. For example, if you look at the first initial solution, which is the one we first mentioned, the tag in 43, this is something, a value which is in between, which is 20. This is really just to stress the fact that the formula is not an exact solution, and you never get with only one value. So you need to carry out a sort of a sensitive analysis to understand how reliable is your final result. Now, of course, this is a presentation of all the theory behind the bearing capacity. We will also carry out a few exercises with numbers in order to let you become a bit more familiar with the use of these expressions. Okay, but let's, for example, have a closer look. We mentioned to the influence of the groundwater table. Now, why there is an influence in which sense? In the sense that, you know, the groundwater table will affect even the weight of the soil. Okay, so if you have, for example, your expression Q lib, and you have, as before, 1/2 gamma B and gamma plus C and C plus Q and Q. Now you have here gamma, you have, this is gamma D, and so you have different gamma which might be affected by the groundwater level. Now, important thing is to remind you to stress the fact, so this is D, and this Q is this gamma times D. Now, if now we will see the difference which is of the groundwater table. This gamma is this gamma. Now, if the soil is the same, there is no difference in gamma. But if the soil is different, remember that the gamma in the overburden pressure here is the gamma of the soil at the side of the footing, whereas this gamma is the gamma beneath your footing. So if you have, this is gamma 1, and this is gamma 2, this is gamma 2, and this is gamma 1, which can be different, because the two terms refer to different types of soils. Now, let's consider the case 1. Let's start with the case 1, in which the depth of the groundwater table is 0. So this means, now irrespective of the drawing which refers to case 3, this means that your groundwater table is here. All the soil is fully saturated. In drain conditions, you have to put here gamma prime and here gamma prime, because you are in drain conditions, effective stress term, effective unit weight of soil. If you have the second case, this was case 1, the case in which, case 2, your water table coincides with the bottom of your footing. So here, this soil is fully saturated, this soil is not. So you see, in case of Q, you will use its gamma, not gamma dash, you will use your gamma, gamma 1, whatever it is. And here you will use, once again, the gamma prime, because here you are in drain conditions, and you use the gamma dash. In the case 3, which is the one you will see in the picture, where the groundwater level is well below, here, case 3, when it is well below, there is no influence of the groundwater table, you will use the normal unit weight here, gamma 1, the normal unit weight here, gamma 2, because there is no influence of the water table. Now, what does this mean, well below? Well below the effect of your possible slip surface, your failure mechanism. Now, if we superimpose our failure mechanism, this is probably more or less the size. We know the size of this footing, of this failure mechanism. If you have, this is B, this is typically the depth of the mechanism is about between B and 2 times B. So, for example, if you have the groundwater table which is deeper than D plus B, this means that this does not affect the failure mechanism, and so you can consider that there is no effect of the groundwater table. Now, why is it so important? Because, for example, your gamma dash is the gamma saturated minus gamma W. So gamma dash is more or less half than the gamma saturated. If you have only this term, and you put gamma dash or gamma saturated, you end up with a limit pressure which is twice as much, depending only on gamma. And irrespective of everything we have just said about n gamma, which is function of phi. Also, this can affect your bearing capacity. So it is very important that you select the correct gamma value, and you have also to consider that if you have a footing and you consider that, well, my groundwater table is well below, so I consider gamma saturated or the gamma, not a gamma dash, and you end up with a limit pressure which is a specific value. Then the water table rises up for its own reason, any possible reason. Your groundwater table rises up to here. Your limit pressure, everything else being equal, will drop because you have gamma dash instead of gamma saturated or the natural unit weight. So the groundwater oscillation can affect the capacity of your footing without you doing anything. When you design your footing, you have to consider where is your groundwater table and if this can vary over time, because this will affect your bearing capacity. Now, you see, this looks very long, very tedious, and in fact it is very boring, but this is the case when you want to extend the application of this simple formula to a general practical case. Because remember, we said this is for applying the limit equilibrium or the upper bound theorems, so everything we have distinguished, separated drain and undrained conditions. But in any case, in this formula, we have made also other assumptions. For example, that the load is vertical, distributed. The resultant here, Q, is centered and vertical. Typically, you will have also horizontal components of the load. Typically, you will have a resultant which is inclined and eccentric with respect to your axis. You can have a ground surface which is not flat, is not horizontal, okay, because you are on a slope. The footing itself cannot be horizontal, but can be inclined, and this is typically not for buildings, but if you think bridges, for example, you will have a footing like that, and you have the bridges like that, so the footing can be inclined. This was assumed for a straight footing, so for a footing which is infinite in length, where L is much greater than B, because infinite does not exist infinite, but when L is much greater than B, so this is a strict footing, you have the solution. What about if the footing is a square footing, for example, in which L is equal to B, or it's a circular, rectangular, is not a strict footing. So all these very trivial, simple, possible differences from this formula must be taken into account. The usual standard approach is to use this general formula, which was suggested by Hansen in the 70s, which is not very satisfying, but it is still much used because it's relatively simple. How does this work? You see, you still have your three contributions. If you look, for example, the first term, you have your Q lim, you have 1/2 gamma B and gamma. So this is your starting point, which is this term. And then you multiply this term, but also all the other terms, by factors, correction factors, which take into account all these deviations from this starting formula for considering other situations. So you will have an S gamma, which is called a shape factor, which consider the case in which the shape of the footing is not a straight footing. This will be 1 if it is a straight footing, will be different from 1 if it is rectangular, circular, or whatever. Then you can multiply by I gamma, which is an inclination factor, which consider that the resultant of the load is not vertical, but it is inclined. Then you can multiply by E gamma, which takes into account that the resultant is not centered in the center of gravity, but it is eccentric. It does not appear that, I will show you why. You can consider B gamma, which is in the case the footing is inclined, or G gamma if the ground surface is inclined. And the same for all the other contributions. For example, so you add up, this is Q and Q, and then you have SQ, IQ, you don't have these eccentric terms, you have BQ, you have GQ, but then you have a depth factors, which is DQ, which is called D. So each single factors has been derived separately from the other, independently. Most of the time they are empirical or based on small-scale tests, typically not in a centrifuge. So you end up with an expression with all these factors, each one determined separately, which is not that satisfactory, because your value depends on the combination of all the uncertainties that you put together. Of course, most of the time you don't have all these factors, unless you are very unlucky and your foundation is inclined, in an inclined slope, the load is inclined. So, but you can run, once again, a sensitive analysis and consider how much this can affect. Then you might end up with a value which is really very small, because all these correction factors are typically less than 1. They will tend to reduce the limit load, the limit pressure, when you have different conditions. So except for the depth factor and possibly some shape factors which can be greater than 1, all these will tend to reduce your limits in a way that at some stage you lose control. And I have reported here just an example of shape factors, depth factors, load inclination factors provided by the various authors. And once again, different authors recommend different expressions, and you have to decide which one is the most suitable. For example, you see shape factors, Meyerhoff suggests that these values SQ and S gamma as a function of B over L, which is the geometrical ratio n phi. You might find other authors providing you shape factors which are less than 1. So you have one author, Meyerhoff, for example, which is quite famous, even if not recent, author suggesting an expression of shape factor greater than 1, and other authors suggesting a factor less than 1. So irrespective of the specific expression, these authors do not agree even in a direction they should go, increasing the limit pressure or reducing it. This is a bit misleading. The depth factors are typically not used, but they are always greater than 1. The load inclination factors can reduce significantly the limit load. Of course, if you have a resultant which is vertical or inclined, it is almost immediate that you will have a reduced pressure, because the soil is no longer fully involved in the capacity, but only a shallower part of the soil will provide your resistance. So typically I gamma, IQ, IC are factors which quickly become less than 1. And I will show in a while, as a final contribution for today, a possible and more intuitive approach to general loading instead of these factors. These are the expressions, for example, for inclined foundation factors, sloping ground factors, and what about if the load is eccentric? We can make use of this Meyerhoff expression. Now, this is a rather clever and simple solution, which is more intuitive and less empirical. Let's compare a situation in which you have a centered load and an eccentric load with an eccentricity E. Now, this is the footing B, the footing breadth, and if you have a load with a footing with a centered load, we have found this expression. Now, Meyerhoff says, well, if you have the same everything is the same, just the load is eccentric. And of course, you won't have the possibility that the same soil will provide with the same bearing capacity. This is definitely a worse situation than this, because the footing is loaded at the side, and so there is not the full development of the same mechanism. Mayor suggests, well, why don't you consider a footing of reduced depth, like this, for which the vertical load is centered. Now you have a reduced breadth B dash, which is B minus 2E, twice the eccentricity, for this footing the load is centered, and you can then apply this expression. But in this expression you have to consider B dash, which of course will influence the limit pressure and will also influence the total limit, because then your Q limit is multiplied by B dash, and if you have an eccentricity also in the other direction, because as you see from this picture, if you have a rectangular footing with a double eccentricity on both sides, also L will be reduced in the same way in its direction. So you end up with a footing, which is a footing included by the dashed lines, where the load is centered and with a reduced limit pressure provided by this reduced size. So the Mayor suggestion referred as the effective breadth is quite a clever way of not introducing further empirical factors, but it is the only way between all this list of factors where you act this way. Now consider that this becomes function of the eccentricity, and so becomes function of your resultant of the loads. So if you move, if you change the size, if you change this distribution of load, you can have a different capacity. So now once again, the capacity is not only function of the soil, it's also function of the size of the footing, and in this case also of the eccentricity of your resultant, so of the applied load. And the same way, if the soil is the resultant is also inclined. So let's now, are the factors in case of in undrained analysis. You will find in all textbooks all these tables. But being empirical, once you have understood the philosophy of the approach, there is no way of going into details and reading all this expression. Let me go to this final in our last slightly less than half an hour. Something which is a different approach from this standard one, which, as I said, makes use of all these factors, and try to follow a different approach, which here it says recent developments, but it is quite now well established for in the last 20 years, and it is not, as you will see, not different from this approach. So it's not a totally different thing, but it is better in terms, in engineering terms, because you don't have just to take one single expression, you put inside, you get with a number, and you as an engineer, you don't know what is the you lose perception of the validity of the value that you get. Now, this mainly refers not to all these factors, but mainly refers to what you can do when you have general loading conditions. So when you have an inclined resultant. Now, if you have a footing, so we try to focus on these factors. So we refer to a limit, Q limit, in a drained material, cohesionless material, on a footing, for a footing which is just bedded. So your limit is just 1/2 gamma B and gamma. You do not have the other terms in this equation. This is the formula that you have for a centered and vertical load. Now, if you have a inclined or eccentric, you will have to multiply this by I gamma and E gamma. And as I said, this can be very much less than 1, and you end up with a value that you lose the perception how good it is. Now, why instead of applying this I gamma and E gamma, you just not make use of interaction diagrams? Now, interaction diagrams is something that you might have come across in structural engineering, where you have a different combination of stresses, for example, along a cross-section of a column, of a pillar, and consider the combination of different load components. So this resultant load, if you have, this is your axis of symmetry, can be considered as a footing where you have a vertical centered component, an horizontal H component, and an overturning moment M. So the two things are absolutely equivalent, statically equivalent. You just consider that you have a footing subjected to 3 different loading components instead of a footing subjected to a resultant which is inclined and eccentric. And this is relatively easy to find out the relationship between eccentricity and inclination angle alpha and the 3 components. Now the 3 loading components are V, vertical, H, horizontal, and the overturning moment applied on the reference point, in a reference point of your footing, which is assumed here at the base, at the contact between the footing and the soil. V is the vertical load, H is the horizontal component, M over B is divided by the footing breadth, so you have 3 loading components which are dimensionally homogeneous, because otherwise the moment has the dimension of the moment, which is not the same as the load dimension. Now, we are looking to the interaction diagram. For example, if we have only H and B, horizontal and vertical components, so we have to find out in this plane the diagram which corresponds to the maximum load. So a combination of these 2 load components which provides you with a maximum allowable, which is provided by this limit. Now this is a pressure, we have to refer to this, but this has been split in the 3 components. So actually, you see in this plane there must be a line, an envelope, which provides you with a maximum possible combinations of horizontal and vertical components. In this case, if you do not consider that there is interaction. So, for example, the plunging mechanism is the bearing capacity that we have discussed so far. So, if the vertical component is not affected by the combination of an horizontal load, you have a vertical straight line. The other possible mechanism is when the horizontal load is prevalent and this footing will tend to slide. So, and this is a different mechanism with respect to this. And so the sliding mechanism will be controlled by the friction between the footing and the solid itself, which is the inclination of that sliding line. But this blue line is in the case that there is no interaction between horizontal and vertical components. And we know from I gamma that actually there is this interaction, because I gamma reduces this value. What is the possible interaction? The possible interaction that you can find, and that we will discuss this, is provided by this red line, which is a curve and is the real interaction between H and V. Vm is the maximum value under a pure vertical load. The red line, a red curve, actually represents an interaction diagram between H and V. Any load combination which lies below the red curve is a safe combination. A safe combination of H and V. If your load combination H and V lies outside the red curve, this means that you are unsafe. And you see, the red line, the red curve, is not like the old blue line. The blue line is in the assumption of no interaction, but the interaction between the two components is strong, is very important. Plotted this way, you have an immediate understanding of the interaction between the two components. Much better than inserting here a factor within an expression that you have seen before, which, as I said, provides you with where you lose the understanding of the mechanism. Now, let's try to find the expression, an analytical expression of that red curve. And this can be provided plotting in this graph, exactly in the same graph, exactly the same expression of I gamma. Because I gamma is somehow showing in a different way, less intuitive way, is showing this interaction. And so using the interaction diagrams instead of using this factor is not different, because you can plot this factor in a way of interaction diagram. Using interaction diagrams is a more insightful and established way of approaching, as I mentioned, already used in structural engineering. So we have also a common approach, and it's not different from using the traditional correction factors. Now, for example, if you take this author, Brink-Jansen in the 70s, which has provided an expression of I gamma, which is the one you see there, that it is 1 minus 0.7 h over v, all to the power of 5, which is a bit, just because it is an empirical fitting of the data Brink-Jansen had at disposal. Now, if you turn around that expression of I gamma in terms of h over v max, it is exactly the same expression, but just plotted in terms of interaction diagram. H and v are the two horizontal components, Vmax is the maximum capacity, the Vmax. If you consider the Q lim for a vertical load, it's 1/2 gamma Bn gamma. In this situation, it's just this. The Vmax, the maximum capacity for a vertical load, is your Q lim times the area. So Vmax is exactly the limit pressure for vertical load, but just expressed in terms of force. So all this is below that ratio. So that everything is in dimensionless terms. Now, if you see here, you see the situation of an inclined resultant, Q. Instead of considering an I gamma, which is function of the angle alpha, or h over v, you just plot the Briggs-Janssen inclination factors in terms of h over v max versus v over v max. And you see, you end up with a curve which looks very similar to the red line we had in the previous slide. So I had plotted just as a qualitative terms. Now you have an analytical expression of the interaction between the two components provided by Briggs-Janssen expression. And as you can see, you have an initial tangent of this expression that it is 10 over 7, which is greater than 1. So it means that the arc tangent of that expression is greater than 45, let's say 50 degrees. So you have an angle of the initial tangent which is 50 or 55, I don't know, whatever it is. But this is not possible, and it is not conservative, because remember, when you are at a very low vertical load, you have a sliding mechanism, and that tangent should not be greater than the friction between the footing and the soil. And that friction delta between this and this can be, say, around 30, 35, depends on the soil, on the roughness of your footing, but cannot be 50. So this means that plotted this way, you realize that if your load combination is close to the origin, for high inclinations, the Briggs-Janssen formula, which is always used and considered even over-conservative, is not conservative. It's definitely not conservative on close to the origin of axis. So this way of plotting this expression is more intuitive, but also shows you that can be non-conservative, close to the origin. Now, how does this work? You plot your combination of H and V in this plot. If it lies inside the surface, you are safe. If it is outside, you are not safe. And the closer you are to the surface, the less safe you are. So it's just a different way of plotting the same information, but in a better way. Now, since this is not conservative, we can do a bit better. So my name is here just because I started my studies working on this, you see, ages ago, last century. But I provided, this was my PhD thesis, another possible expression which takes into account a beta tangent. It's not that much different from what Briggs-Janssen provided, but just solving this problem of the initial tangent. And of course, after myself, many other authors have provided other possible analytical expressions, but conceptually, this is really just a different approach, the use of interaction diagrams with respect to the inclination factors. And another good point is that in the same way you can approach the M component. So the case we have analyzed here, in which the footing, the load is vertical, but eccentric. So you have the vertical component, no horizontal, but overturning moment. And this can be approached in the same way. And you end up with an interaction diagram in which you have the vertical load here and your moment divided by B. And then you have another sort of parabola which separates safe load combination inside your curve from unsafe loading combinations outside the curve. And this expression, where does it come from? Exactly from the measure of concept of the effective breadth. Nothing new. If you plot this thing, which I have showed you, in these terms, you can turn it around and show that the measure of concept of effective breadth plots like this in this interaction diagram. So you can use the two deviatoric components, horizontal and overturning moments, deviatoric from the vertical loading components, in the same way. And you can also put together in a no longer a plane where you have a V and M or V and H, but in a space of the loading components. A 3D space of loading components where you have V, you have H, and you have M. And you end up not with a curve, but with a surface inside which you have all the load combinations, safe, and outside which you have unsafe load combinations. So you can, once you know which is your surface, failure surface, and you know your load combinations, you can play with your load combinations, trying to be more safe. This is, for example, one possible expression, depending, you see, only on three factors, which more or less comes from this or come from other experiences. As I said, this comes from other experiments which I carried out long ago, and I derived these parameters, but you might have different expressions with different parameters, or you can use I gamma and E gamma, whatever. So this is something we know. We know the failure envelope. We just have to compare our load combination with this possible outside failure envelope. Now, for example, you can see here, this is a section, this is a transversal section at V constant, V over V max is 0.5. So this is a transversal section. Consider that you cut a slice normal to the V-axis of this failure surface. And you see that the section is a sort of an ellipse, but this is a rotated ellipse, taking into account that the situation at the left-hand side compared to the situation on the right-hand side are different. Now, at the left-hand side, you see you have the inclination and you have the eccentricity with the same sign. They act together. Whereas on the right-hand side, you have the same inclination, same eccentricity, but on the other side, opposites. And so the eccentricity and the inclination act together in a different way. They combine and provide you with a capacity which can be twice as much as the other capacity. Now, if you use this expression, you end up with something which is irrespective of the direction of the eccentricity. So this formula does not allow you to consider the different sign of the eccentricity, whereas the interaction diagram do. And finally, This approach enables you to have a suitable and more reliable definition of safety factors. This is the final slide. Let's, for example, consider only an inclined load. So we are in the HV plane. You have your external maximum envelope, and your point, your load combination, lies in B, because you have an important vertical load, which takes you to A, and then you have a possible horizontal loading component, which takes you to B. So you are in B, and you get to failure when you touch that failure envelope. But you can touch the failure envelope in 1, in 2, in 3, in 4, whatever. Depending on what? Depending on your load path. Will you get to failure just increasing the horizontal load and keeping constant the vertical component? You will go from B to G to 2. But then you are closer to 1, to the point 1, if you go, for example, to 1, reducing your vertical load. And depending on your structure, you can get any of those possible load paths. Now, when you define, using this formula, you typically divide this value by an overall safety factor, you consider that the ratio between H and V, this I gamma, stays constant. So you implicitly assume that your load path is number 3. You go from O to B to 3. If you divide this by a factor of safety, which is what you typically do. And this is, of course, not the worst situation. So if you do not use this approach, if you do not consider different possible factors on different load combinations, you lose once again the perception that your factor of safety depends on your load path. And this is something that if you divide this by a factor of safety, once again, you do not consider. And finally, if you want to use the partial safety factor approach, which is what we typically do with the new Eurocode, for example, that you use partial safety factors to the soil parameters, and you amplify the loads, then you see if you reduce your soil parameters, you have a strength reduction. From the dashed line, you reduce your failure envelope to the black line at the bottom graph. And you can increase your load, taking into account the uncertainty that you have on B and H, for example, so you can amplify the load. And you can, on this plane, play games amplifying the vertical component, the horizontal component in a different way. So this approach allows you to make use of partial safety factors like for as required by the Eurocodes. So this was really just the beginning of the story, which I told you, my case started many years ago. But this approach, for example, now is the typical standard approach used for the design of offshore structures. Offshore structures are quite different from onshore structures because they are subjected to very relevant horizontal load and overtrailing mode. If you think of a platform in the middle of the sea, it is relatively light structure compared to wind loads, wave loads, which will apply both horizontal and moment load. And capacity, in that case, is extremely relevant because you might have storms which in the past have completely produced the failure of these structures. So you cannot rely on this type of formula. to design that type of advanced structures. So now the standard way of design of offshore structures and all structures where these deviatoric loading components are extremely relevant do follow the interaction diagram approach and all the modeling which follows this approach, which I'm not now going to the details because it is something advanced, but it is important now that these days you know that we can do better than this general formula. Okay? I think that's it for today, and see you next week.